Today we're going to start doing problems using the capacitance formulas and actually see how to do some of the math. So our first goal is we're going to have a capacitor whose plates are 20 centimeters by 3 centimeters and separated by a 1 millimeter air gap. You might say, well, that seems rather long compared to the width. These are probably rolled up. So our first job is to take a look and say, okay, it'd be 3 centimeters by 20. Our first job is to get the area, and we really should do it in meters. So it's 0.2 meters, because this is just length times width, just like in regular math. It's 0.03, and let's see how many square meters that is. 6 times 10 to the minus third. Let me write that in regular number in expanded form. 0.006 meters square. So that's our area. So to get the capacitance, we have to use that 8.85 times 10 to the minus 12. That's the constant. Times the area, which is also a very small number. Now the separation is a millimeter. A millimeter is 10 to the minus third. So we're just going to do 1 times 10 to the minus third, and we don't have to square it or anything like that. So let's put the funny e in the calculator. Divided by 1 times 10 to the minus third. And I get 5.31 times 10 to the minus 11 farads. Now, that's not a convenient way to write it. So what we do is we take 5 times 10 to the minus 11 farads, and it's 1 times 10 to the minus 12. Farads is a picofarad. So that should work out to 53, it's actually 53.1, but we'll just go 53 picofarads. And you say, well, that's a terribly small number. Yeah, but that's how capacitors are rated. Then if we take a look at the next thing, we're going to attach it to a 12-volt battery. And we say, well, what's the charge? So we're going to hook up these plates to 12 volts. And let's see what that is. So to do this, we're just going to use QVC. And it's delta V, which is the change, but it really is just the V or the voltage. And this is really easy. So it's a 12-volt battery times the 5.3 times 10 to the minus 11. We'll just use regular farads because we really should. So 12 times 5.3 to the minus 11 is indeed 6.4 times 10 to the minus 10 coulombs. So remember, coulombs is a charge unit. I don't know if we've talked about that in a while. Now we want the electric field between the two plates. So we use this formula that we've seen, but we haven't actually done any math with it yet. So the delta V is the electric field times the distance or the separation. So E is delta V over the separation. And we said this was a 12-volt battery, and it was 1 times 10 to the minus third was the separation. So 12 divided by 1 to the minus third is 1.2 times 10 to the fourth volts per meter. Now, that's a new unit that we're seeing, because before what we saw was Newton per Coulomb, but volts per meter is also equivalent. In fact, volts per meter, I think, is the one that's used a little more commonly. Now let's do a different capacitor. So we're told the spacing between the plates of a 1 microfarad capacitor is 0.05 millimeters. and they want the surface area of the plates. So to do this, we're going to use this formula. Now we want the area. The bigger the area, the more capacitance. So our capacitance is micro, let's see, which is 10 to the minus 6, because nano is 10 to the minus 9. The distance is 0.05. Now that's millimeters. So we're going to go 10 to the minus third meters and divide it by that ridiculously small number, but that's what the E value is. Oops, we want the area, not the C. And let's see what it is. 1 times 10 to the minus 6 times 0.05 to the minus third, divided by 8.85 to the minus 12. 5.65 meters squared. That's a pretty good area. This almost certainly is a rolled up capacitor to get that kind of area. Now we want the charge. And we're going to hook it up to a 1.5 volt battery. So we're going to hook up this capacitor just up to a normal, like a AA or AAA battery, or even a D battery. They're all 1.5. Now you might say, well, what's with all those batteries and why do they have different letters if they have the same voltage? A D battery just lasts longer. Think about a D battery. It's really big. It has more chemicals inside of it. It just can do more because it can last a little longer. So this is pretty straightforward using QVC. So what do we want to solve it for? The C. We want the Q. We want the charge. That's the capacitance. So it's a 1.5 volt battery. The capacitance is 1 microfarad, which is actually a pretty strong capacitor. It's 1.5 times 10 to the minus 6 coulombs, or 1.5 microcoulombs. Either would be acceptable. Now, let's see. No, that's the same problem. I just have it on this plate or page so we can see it. Let's say we want the electric field. And just to remind ourselves, if you have a plate that's charged, let's say positive on this side, you have to have another plate on the other side that's negative. And the electric field always points from positive to negative, because the positive person gives out from themselves. So these are some pretty easy calculations. It's just a matter of remembering things and remember which ones to use. And the distance is 0.05 times 10 to the minus third meters. So let me just double check, make sure we're okay. Yeah, and that's 3 times 10 to the fourth, or 30,000 volts per meter. Now here's something we haven't done a whole lot with, which is, well, what's the number of excess electrons? How many electrons are the plate? And could we actually calculate that? And we can. Because we remember one electron takes a charge of 1.60 times 10 to the minus 19th coulombs. And that's the fundamental charge. I just have to go back to see, well, what was our charge? 1.5 times 10 to the minus 6th. So we have a charge of 1.5 times 10 to the minus 6 coulombs on the plates. And one little electron is 1.6 times 10 to the minus 19th coulombs. So let's see what happens there when we put it in our magic number machine. Okay, 9.38 is fine, times 10 to the 12th electrons. And I believe that number, it's not unreasonable. one thing to note is that's not even a mole of electron, because that's not even up to 10 to the 23rd. What would be the problem if we got a fraction? If we got like 0.4 electrons? We should know we did something wrong. Now the reason if we got 0.4 electrons, I'll write it down here and we'll cross it out, is because you cannot have a fraction of an electron. One electron, one bare electron, or one bare proton with that charge 1 times 10 to the, or 1.6 times 10 to the minus 19, that's the smallest charge that exists free in nature, as far as we know. So if you get a fraction of an electron, or 10 to the minus third electrons, there's a problem. It has to be a positive. It can't, or not only positive, it can't be a fractional number.